Okay, welcome everyone. I guess there's still a few people coming in. How is everyone? I hope everyone is well, and hope you had a good weekend. Um, and this week unfolds to be quite positive for everyone. So I'll open up the questions. This is the agenda that you see before you for today. And I just stress that the first midterm is next Thursday, October 8th, from 7 to 9 p.m. And if you still have issues or problems with that conflicts, just let me know via email. And of course, there'll be the Wednesday discussions this week and next week as usual. And I'm always available if you need help with questions. So today, so are there any questions about what we covered up to now at all? Okay. So then I'm going to continue today with our discussion. And today I want to introduce enthalpy, which is something everyone has heard about because you've always seen things like delta H of reaction, and often these are enthalpies of reaction. And often you'll see it in this form, which is the standard state enthalpy of a reaction. So today I want to introduce that, and you'll see that enthalpy, just as we wrote the energy U as a function of temperature, volume, and the amount of substance present in the system, you'll see that H arises naturally as a function of the variables temperature, pressure, and often we like to use pressure when we work in experiments because temperature and pressure are very easy to control, and so it seems natural to have those as your variables. And the most ultimate function of thermodynamics that uses temperature and pressure as the natural variables is the Gibbs free energy. And so Gibbs free energy, G, as you may have seen before, is the ultimate thermodynamic potential. It's very powerful and very useful, and we'll get to that. Okay, so today we're going to talk about, I'm going to introduce enthalpy, and then we'll look at the total differential of enthalpy, knowing that it's a function of temperature, pressure, and in the sense that we can write it as that, as it will be a state function. And finally, we look at the Joule-Thomson experiment, which is an analog of the Joule-free expansion that we discussed last class. And it will tie into two concepts, one relating to total differentials and the other as an experimental tool, the Joule-Thomson experiment. Okay, so let's begin with enthalpy, and this is a very quick and a very obvious way to introduce enthalpy. We'll call it H for now. And it's going to be a state function. And the way to do it is we start with our first law, okay, which we know is du is equal to dq plus dw. Okay. And now, if we make two stipulations, so our stipulations, or we could say constraints, but let's stipulate, okay, that we have something that's reversible, so a reversible process of any kind, and two, constant pressure. Okay. So because of constant pressure, any differential of P is going to equal 0, okay, because of constant pressure. Okay. And hence, delta P for anything will also be equal to 0. But dP is what we're interested in because we want to write this in differential form. And because the process is reversible, we know we can make a substitution for the external pressure when we deal with work. And so what we have here is du is equal to dq. Now I'm going to write this subscript P here to indicate that this heat interaction between the system and the surroundings is at constant pressure. Okay. That's why we have that subscript, because we know Q is a path-dependent function. So we have dqp. And then since this is a reversible process, what we're going to write here is minus P as a function of temperature, volume, and N, which may be given as an equation of state, times dV. And now I'm just going to write for the rest of this lecture, P of T Vn is just as P, okay, to save space and to make things a little bit more clear. But I just want you to know that this is what this guy is, okay? So now what we can do is rearrange things. So we can write dQp is equal to du plus P times dV, just by bringing the term minus PdV to the left-hand side and isolating dQp. Okay. Now we can do a little game here. Okay. We can use the chain rule to look at something. So if we wanted to take, if we had the product, so this is a product, it's a multiplication of two things, pressure times volume. So that's our product. And we know that pressure and volume are variables, or they can be functions, just because here we see that pressure can be a function. So if we wanted to take the total differential of this product, so let's say we wanted to have d of PV, which is the total differential of the product. And so dPV is analogous to some du, dt. It's the same thing, but now we've replaced u or t with this product PV. That's all we've done. Okay, so that's all we're doing, nothing more complex than that. So writing d parentheses PV is saying that we want to look at the total differential of this product. Just as if I wrote dt, I would be interested in the total differential of temperature, or du is the total differential of u. So dPV is the total differential of the product PV, and we can use the chain rule from our calculus course, and the chain rule says that we just take this will be a sum, and so we can write this as PdV plus VdP. It's just the product rule. Which is you take the first, hold it constant, and take the total differential of the second element of your product, and then do the same, just reversing the roles of the two things in your product. Okay, so we can write dPV in this manner, okay? But since dP is 0 in our constant pressure case, but we have stipulated dP to be 0 because it's a constant pressure process. Hence, dPV is equal to P dV only because that dP term is 0. Okay? So if we go back to our expression here, okay, we can make some substitutions. We can say that dQp is equal to du, but now we have this PdV term, but that PdV is equal to dPV. Okay. So now we have the sum of two differentials, two total differentials. This is the total differential of u. This is the total differential of this product PV. And what we're going to do is combine them. And we're going to combine them into one total differential. So we know that taking the derivative of two things is just, it's additive, it's linear. So we don't have to worry. What we can do here is write d of u plus PV, right? So if you wanted to take the derivative of a sum, that's very simple. Differentiation is linear, so that you would take derivative of the first term plus the derivative of the second term, right? So this would just be du plus dPV, but of course that's just what we started with. That's why I wrote the equality. Okay. So what we have here now is that dQ sub P, this heat interaction at constant pressure, which is equal to du plus dPV. Now this is stemming from the first law. Again, I just remind you, this stems from the first law and the fact that we have constant pressure. Okay, so those are the two things, and of course it's reversible. So all of these three things lead to this expression. And then finally, the properties of derivatives allow you to write the last part, which is in red, this total differential of u plus pv. And so what we arrive at is dq sub p is equal to d of u plus pv. Again, under the conditions I've noted right here. So these are very important under these conditions. Okay, those are the conditions or the stipulations or the constraints that have to be met. But now, maybe you see something that you've seen before. We can define something. We define now H, which is defined as the enthalpy U plus PV. Okay, so H is the enthalpy. Okay. And that's a new thermodynamic state function. And so this total differential, dQp, is equal to dH, just as we have here from this term right here. Remember, d times d of whatever's in the parentheses, which now we've defined as h. So what we have is this guy, dq sub p is equal to dh. H is the enthalpy. This is reversible process. Constant p. Okay, and this arises, of course, from the first law, but I don't need to write that here. So that's all right. So this is the enthalpy. And you can see here that enthalpy is a state function. Enthalpy is a state function because it's path independent. Okay. Well, it's kind of, if you just look at the equation, it tells you everything you need to know. U is a state function. It only depends on the two end equilibrium states that you're interested in, or if you're looking at a system at equilibrium, the energy of that system just depends on that state. You can bring it back, you can take it away from that equilibrium state through any process you want and bring it back. Delta U will be zero over that cycle. And it doesn't matter how you prepare that system at a particular equilibrium state, U will always be U. And obviously pressure and volume are state functions. If you take a system from equilibrium, perform some process on that system and then bring it back to where it was initially, delta P and delta V will be zero. And hence those two are also state functions. And since U is a sum of state function, sorry, H is a sum of state functions, enthalpy is a state function. It's also path dependent. Okay. And under the conditions of a reversible process in constant pressure, enthalpy, changes in enthalpy are related to heat interactions. Okay, so the heat interaction at constant pressure, dQp, dQ sub P is equal to dH, which is the enthalpy change in the system. And this is why when you were introduced to calorimetry perhaps and thermochemistry or earlier on, you can write delta H as a heat of reaction because you carefully control pressure. Obviously, this would be at a particular temperature. Delta H's are temperature dependent. You can measure enthalpies of reaction at different temperatures. And that's a kinetic phenomenon that you get different, it's coupled to kinetics, that you get different delta H's at different temperatures. So you see here that this delta H of reaction then, that you've always, I hope you've seen before, and I can sort of introduce now and we'll show later that it's a function of temperature, really is this heat of reaction that occurs at constant pressure. Okay, and the connection comes through this relationship that we just derived, okay, that we had to start with way back here from the first law, and then we derived everything in terms of how enthalpy arises. Okay, any questions? So enthalpy arises as this heat of interaction between the system and surroundings at constant pressure, and it is a state function. Any questions, comments? Okay. All right, so I'm going to move on now to looking at the total differential of H. So let's take a look at the total differential of H. H must be a function of some variables. So enthalpy, H, must be a function of some variables, just as U was. Okay? And let me remind you, let me just sort of put here that delta U of a reaction, okay, is going to be equal to what? Does anyone want to guess? What heat interaction would this be? Use of B. Because recall from the first law, du is equal to dq plus dw. But if it's at constant volume, the dw term would vanish. Because remember, dw is minus p external dv. And if it's constant volume, dv is 0. So we see here that delta U of a reaction or delta U of a process at constant volume would just be equal to the heat interaction at constant volume Q sub V. Okay, so enthalpy and energy U, H and U are analogous. There are a lot of parallels between the two. And the thing that distinguishes them is that one is at constant pressure, one is associated with processes at constant pressure, that would be H, and the other is at constant volume, which is U. Okay, so that's something to keep in mind. Okay, so getting back to this idea that H must be a function of some variables. Well, temperature is obvious. We need to include temperature, and I've sort of intimated that using expressions like this, that H has to be some function of temperature. And now, since we sort of started our discussion by a stipulation or a constraint that pressure is involved, pressure is constant, it must mean, or it suggests that pressure would be some sort of natural variable to use to control H, to let H be a function of, or to let H depend on. Since we saw that H arises when we control pressure, we should probably have that pressure as a variable that H depends on. So we're going to consider now that H is a function of temperature and pressure, and obviously H will be extensive. I haven't said anything about the intensive nature. And that also, the fact that H is extensive comes from the fact that heat, since we've defined H in terms of heat, and heat is not a specific thing, heat is just an amount, right? Through this expression, heat is just an amount. And so since we're equating delta H to some amount, we haven't made any connection to H being intensive, meaning independent of the amount of substance. So H turns out to be, in its most fundamental form, extensive, an extensive thermodynamic function, or these things are called potentials, and you'll see a little later why they're called potentials. So H we can write as a function of temperature, pressure, and N, and for the moment we'll let N be constant. Okay, so we won't worry about anything that allows for the changes in H with respect to N. We'll get to that later. So now what we're interested in, if we know that H is a function of temperature and pressure, and N, what is H, and what is the total differential of H? Okay, where N is constant. Okay, that's what we're interested in. And just as we did for U, we can write in an abstract way what dH is. dH of temperature, pressure, and N is just a partial derivative of H with respect to temperature, constant pressure times dt. And in fact, I really should put an N there, but I haven't been. But I think everyone would, at this point, I hope everyone realizes that N is a constant, so we can put it there. Plus partial of H of temperature, pressure, and N with respect to pressure, a constant temperature, N times dP. And since dN is 0, a term like this, partial of H with respect to N, a constant temperature, pressure, dN, would be 0. We don't have to worry about how H depends on N because we've stipulated that N is a constant And so this guy would equal 0. Okay, so we're not going to worry about that term at this point. So don't worry about it. All right, so we have dH in its most general form for the moment. Right, so this is the total differential of H. Any questions on that or comments or any discussion? And you'll see here that this is what we saw by analogy to U. Remember, I'm just going to write this to recall, to refresh your memory perhaps. But now we had volume instead of pressure. Sorry, T. Okay, so that's what we did last class with the Joule-free expansion and the discussion of that, and I introduced you to that. Okay, so we see here some parallels. Just as we saw for U, you write the total differential of H. Okay, any questions, comments? Okay, great. So a few points. Point number 1. Okay, so this is something to think about on your own or reflect if it's not clear right now and you don't want to discuss it right now, or if you feel comfortable just thinking about it on your own, that's fine. Okay, so very important that you understand why we can write this and the analogy to U. Okay, so point number 1, constant pressure. Constant pressure. Okay. dP is 0. Okay, so let me also stipulate that these two relationships right here are general. So these guys, okay, they are general. They're very general, and so they will always hold. Okay, as long as a dN is constant. All right, so point number 1, going back to this, at constant pressure, dH of temperature, pressure, and N, the dP term is going to vanish. So all I'll be left with is the partial of H with respect to temperature at constant pressure. That's okay. Now remember, in this expression, that total differential expression, I would have another term here, which is the partial of H with respect to P times dP. But dP is 0. Okay, so we don't have to worry about that term. The other thing we have here is that at constant pressure, dH is equal to dQp. Remember, this is what we found here at constant pressure. This is what our discussion was. So dH is equal to dQ sub P at constant pressure. So we can write two expressions here, this one and this one, at constant pressure. Again, I remind you, we have constant pressure. Okay, but we know what dQ is at constant pressure. We've seen this expression for dQ sub P a few weeks back when we were looking at heat interactions, and dQ sub P is equal to C sub P, this path-dependent heat capacity, the constant pressure heat capacity, which is a function of temperature, times dT. Okay? So now we have another way of defining this constant pressure heat capacity. Earlier on in your courses, you may have been introduced to heat capacity just purely from a phenomenological point of view, where Cp was given or defined for you through an equation like this. dQ sub P is equal to Cp dt, or in another form, Q sub P is equal to Cp times delta T. You may have seen both of these forms earlier on, most likely this one. Okay, and that's how you were introduced to Cp and what it means. Okay, now we're going to see a more fundamental definition of Cp that arises from these two expressions that we've derived beginning with the first law of thermodynamics. So these two expressions, again, when you go back to look at these, this lecture, you realize that they arise from the first law. Okay, we started with the first law. So one of the things that I will tell you now, and keep this in mind, write it down in your notes or on your board, right, is that everything from now is going to stem from the first law. All of the equations that we will, or most of them that we face or encounter now will be in some way related to the first law. It's pretty amazing. Okay, it's pretty amazing. So now let's go back to this. dH is equal to Cp of T dt. Now what we can do is look at the equivalence of this expression and this expression in this form. We have Cp of T dt. Okay, we look at the right-hand sides of the equal sign in both cases. So for the second equation, we have Cp of T dt on the right-hand side. And on the equation above on the right-hand side, we have partial of H with respect to T, constant pressure in N times dt. And we can see an equivalence now. Okay, we don't worry about the dt terms on both sides. We look at what else is there. And what we find then, right, is that partial of H with respect to temperature, pressure, and N with respect to, sorry, the partial of H with respect to T at constant pressure and N is defined now as the constant pressure heat capacity. And so this is the rigorous thermodynamic definition of the constant pressure heat capacity. See, we see here now again, Cp is related to H. Just as Cv was related to U, and I'll remind you of that. Remember from last discussion, last class, the partial of U, which we define as a function of temperature, volume, and N with respect to T, a constant volume in N, was defined to be Cv of T. So you see here the analogy between H and U. Okay, so these are the fundamental thermodynamic definitions of heat capacity. Okay. Any questions or comments so far? Okay, so just as I did for U, I've written the partial derivative of H with respect to temperature in terms of something that's experimentally measurable. So Cp and Cv are experimentally measurable. So you can measure these properties of a system, of a substance in the lab. Okay, so you can arrive at them experimentally. Any questions or comments? Okay. But what about, let's go back to the total differential of H. Okay, so let's go back to dH, just as we did for du. And we saw that dH, the total differential, is partial of H with respect to T at constant pressure in N dt, plus the partial of H with respect to pressure at T and N dP. Okay. We just saw that this guy is Cp. Oh, this guy is equal to Cp of T. So we can write then that dH is equal to Cp of T dt plus the partial of H with respect to pressure at T and N times dP. All right. This is where we are so far. And you'll remember this is exactly, by analogy, what we arrived at for U. And let me again refresh your memory about that analogy. We saw that in this case we had Cv of T dt plus the partial of U with respect to volume. Remember, we use volume for U, not pressure. Constant Tn times dV. Okay, so that's the analogy. that we had with U. And so again, Cp and Cv are experimentally measurable. Okay, so if I had a process and I wanted to find delta U's or delta H's, I have one half of my problem okay or solved, because I can get this term and this term, okay, by integration. But the problem is I don't know what dH dP or what we saw last class, du dV are. We have to find ways to obtain those derivatives or those rates of change of those thermodynamic functions with respect to pressure or with respect to volume. And for the case of U and its dependence on volume, we use the Joule-free expansion experiment. We use the Joule-free expansion experiment to arrive at what du dV is in terms of experimental measurements. So today what we're going to do, and does anyone remember what that special characteristic was of the Joule-free expansion? For the Joule-free, the characteristic for the Joule-free expansion was that du is equal to 0. And that's why we could arrange or rearrange this expression, because du was 0. It was an isoenergetic property process. Okay, the energy remains constant. There is no change. And because of that, we could rearrange this expression and then devise a way of obtaining this partial, the partial of U with respect to V, in terms of experimental measurables, which were temperature and volume. Today, we're interested in the question, what is partial of H with respect to P? Is there any way we can devise an experiment in which we can do the same trick? Is there any way that we can devise an experiment in which dH is 0? Because if dH is 0, we can use this top equation, the equation above the one that's in blue, to rearrange that equation and obtain this partial of H with respect to P isolated in terms of things that are experimentally measurable. So you can see here that if dH is 0 in this top equation, right, what we have left with is 0 is equal to C sub Pt times dt. Well, we can measure Cp in an experiment. Maybe you have already in earlier labs. We can measure T. This partial derivative, partial of H with respect to P, is this problem derivative, but that's okay. And then we have P at the end, dP. And of course, P is something that we can measure. So if dH is 0, we can isolate this partial derivative and then get everything on one side that is experimentally measurable. This is what we did with the Joule-free expansion for U. We said, well, in the Joule-free expansion experiment, delta U or du is 0. So that's going to allow us to rearrange this expression and obtain this partial of H with respect to P, or partial of U with respect to V. So let's do that. So is there any experiment that allows us to say that H is constant, process where we have no change in enthalpy? Indeed, there is. Okay, so the question now is, what is partial of H with respect to pressure at constant temperature in N? Remember, there's no H meter, and likewise, there is no U meter. Okay, and you'll see later that there is no G meter, where G is the Gibbs free energy. And if you've been introduced to the Helmholtz free energy, there's no Helmholtz free energy meter either. Okay, we have to get at these guys in a different way, okay, indirectly. Okay, and so this is the question now we're going to answer. Okay, any questions? Anything you want to discuss at this point? Even why we're doing this?
So I just want to make sure that for this DH equation, this is just for constant pressure, right?
Which DH? The black? This
Yeah,
one?
the black. The black one, like we established at the beginning that this was for constant pressure. I just want to clarify that this is still holding true.
No, no. So this expression is general.
Okay.
So this expression, the one at the top, okay. Ooh, what did I just do? I don't want that. This expression at the top is a general expression, and it arises from our general expression for the total differential of H. So this thing that I just labeled as a blue arrow, now there's two blue arrows. This is a general expression.
Okay. Thank you.
And so what I said is that for that first term on the right-hand side of the equal sign, right? If pressure were constant, this would just be Cp of T times dt, because this would just be dQp, right? At constant pressure, this general equation would reduce down to something simpler. And that something simple is that dH would equal this heat, this dQp at constant pressure. But the equation here is general. That's a good question. I'm glad you brought it up. Perhaps others are asking the same or thinking the same thing. Okay, so did I answer your question?
Yeah, you did. Thank
Okay.
you.
Okay, right. So this is general. All I'm doing now is fitting in the little pieces of this general equation using what I already know about processes that are having constraints in them. Okay, and I can do that because this first term, right, is a partial with a constraint. It's a partial derivative with a constraint. So I can fill in that partial derivative with knowledge of a process in which I had introduced a constraint. Right? So all of these partial derivatives have a constraint on them. So I can fit in pieces from other processes that have that matching constraint. It's okay, but overall, this whole equation is general. Okay. As is the case for du, which is this equation here, which is in blue. Okay. Yeah, does anyone still wish me to continue or try to approach it from a different way? Okay, that was a good question. Okay, an important one. Okay, so let's go back now and look at the Joule-Thomson experiment. Okay, so again, our purpose here is this. This is our purpose for the moment, our very, very short-term purpose, to answer this question. Okay, what is partial of H with respect to P at constant temperature and N? And that's this term right here in this very general expression. Okay, so that's what we're after here. So the Joule-Thomson experiment. Okay. And it's not that simple, not that complicated. It's actually rather simple. It uses as a system a gas. Okay, and so in some sense, it's something we've already seen. And here is the setup. So we have a tube or some sort of a conduit, okay, and it's insulated. So we have an insulated conduit. So this could be a circular tube. It could be a tube of any shape, okay, and it's insulated. So this is our insulation. Okay, and the blue is a conduit, some sort of pipe, if you want to call it, what have you. And what we're going to say is that, oh, right, and in the middle of this, okay, this is going to be a porous material. So this porous material is going to separate two sides of this conduit. Okay, so we have the left and the right. So we have some porous material, and it's porous, meaning that it's going to, so our system is a gas, so we have a gas flowing in this direction. Okay, and of course it's since it's flowing, it's going to have to go through this porous material. And that's why this material is porous. It's going to have to allow this gas to flow through it. But it's porous in the sense that it does offer some obstruction. So if you have a certain amount of, if you have a flow rate on the left-hand side, this porous material, though it won't block all of the gas flowing, it's porous, it's going to certainly slow it down. It's going to cause some sort of obstruction to this flow of gas, but it's not going to prevent the gas from flowing. Okay? So if you have a certain amount of gas coming in on the left, it will all go through the porous material. Okay? It'll just be that there's some obstruction and there'll be some consequences of this obstruction. Okay? So we then have gas coming out here. Okay? So that's what this porous material does. All right, so let's start. So that's the system setup. So on this side, we have some pressure, which is constant. Okay? So on the left-hand side, we're going to have some pressure that's constant. We can call it pressure left. Okay? And on the right, there will be some other pressure. So this gas is flowing through this conduit, and it's coming in at P sub L, P left. But because of this obstruction, there's probably going to be a decrease in the pressure. That's something that is intuitive, perhaps. So on the other side, you'll have PR, okay? P sub R. Where P sub R now is this reduced pressure because of this obstruction presented by the porous material. Okay. There will be a temperature T left. Okay. The system will come in, our gas will come in with certain temperature T on the, and there will be a certain temperature T right. Okay. So this is the flow system. We have some flow going along, and it continues on. We don't have to worry about the very, very far left and the very, very, very far right. Just imagine this thing going forever, okay? And so it does on either side. So what we're going to do now is consider a little bit of this gas, or some volume element of this gas in this process. Okay, so let's think about this. This is our first equilibrium state. So we can say our initial and so what we're going to do is follow a little volume element of this gas as it starts on the left and it goes through the porous material and ends up on the right. So just think of this as right? You're following some amount of volume from the left. Okay? It doesn't matter what that exact volume is. If there's some volume, just imagine you can somehow isolate that little plug of gas. And all you're going to do is watch it as it goes through the porous plug and then goes through the other side. Okay, or I can repeat it. I don't know how I come across on the video. Is it this way or this way? Okay, but does everyone understand the experiment? So all you're going to do is take this, envision you can see this volume of gas on one side, a little plug of gas, okay, and you're just going to follow it as it moves through from one side of this porous material to the left to the other, and I'm going to move from left to right as I watch this. Okay, and the volumes don't necessarily have to be the same, obviously, because the pressure and temperatures are changing on either side of the porous plug. So we're just, you know, this volume can change as it goes through this porous material. So at the initial equilibrium state, if you want to call it that for our gas, here's the porous plug. It will start with the gas volume element on the left. Okay. Here it is. So this is our gas. Okay, so it's at P left, and we have some V left. Okay, now of course, this is P left. There's some pressure that's forcing the gas to move. And so this is a little volume element of interest. Okay, so what I mean is that at the moment I start looking at this system, right, the gas is continuously flowing, but I'm just going to look at this little bit of volume, which has this P left acting on it. Okay, and now I'm going to follow this volume as it goes through the porous medium. And what happens, okay, on the right-hand side, I have nothing yet because this volume element hasn't gone through to the right-hand side. That's why I haven't drawn anything. Okay? But as the experiment proceeds, and of course this is insulated. But as the experiment proceeds, as I indicate here by this red arrow going down, what will happen to that volume, again, all this insulation. Okay, here's our porous plug, approximately in the same position. Okay, now there will be nothing because our volume element has passed through the porous plug, but now our volume element is here. Okay, so now I have the gas at T right, P right, V right. Okay, so there's nothing on the left, but that volume element or the amount of gas that I started with on the left has gone through this porous plug and has appeared on the right. And I've indicated a different volume just because there's a different set of pressure and temperature, so the volume will have to be different on both sides of the porous plug. Okay? So, and of course on this side we have P right, which is the external pressure. Okay, so that's the experiment. Is everyone clear? So the gas is continuously flowing through, but what we've done is say that, okay, we're just going to focus on some volume. And of course, that would mean that there's a certain amount of moles in that volume when we start with, which is here. Okay, so we're going to have some volume with a certain amount of N. Okay, and that certain amount of N is going to pass through with a change in volume. So the change in volume is indicated by the blue on the bottom and the red on the top. Any questions? This is the setup of the Joule-Thomson experiment. We'll look at the equations and the mathematics. I think I won't start that right now, but I want everyone to understand the setup. And so let's just take the final few minutes of the course. If you have any questions or comments about or misunderstanding about the experiment. Okay. Okay. So our system is the gas. Okay. I want everyone to keep that in mind. Okay. So our system is the gas. And one question to you, this gas is going through a conduit that's insulated. It's insulated, as I've indicated through the red dashes around the conduit. So what do you think will be the consequence as it relates to heat interactions between the system and the surroundings? If our conduit is insulated?
The interaction will be zero or low.
Right, it's going to be zero. So that's right. In reality, it will be low, but for the purposes of our course, that's exactly right. Our idealized insulation means that there will be no heat interaction. So because there is insulation, we already know that dq is going to be 0. And we can't really say what this is, dqb or dqp, but it doesn't really matter, right? dqp and dqv were just two different types of processes. There could be many other processes. So I could have any other subscript here. All we know is that there is no heat interaction. So there is no heat interaction for this course, for this process. And so that's important to keep in mind. Okay. Any questions or any comments? That's good. It is insulated and hence there's no heat interaction. We're going to make use of this next class as I continue to discuss the Joule-Thomson experiment. And again, I remind you that the Joule-Thomson experiment in part is to answer this question so that we can fill in the second term in this general expression. Okay. But the Joule-Thomson experiment has a practical side to it too, and I will address that practical side as I finish the discussion next class. Okay, any questions? Any final? Okay, I always ask that. Okay. All right, then. Thank you all for attending the lecture and your discussion and participation. I hope you had a great weekend. I wish you all a great week. And I will be around. I guess I have my office hours, so if you want to discuss anything. And I will end the meeting at this point if there are no more questions.
Thank you.
Thank you.
Okay,
Next day.
thanks. Have a nice day, everyone. You too. Thank you.